You did it without me saying anything. I was going to say, are you recording?
On top of your job. I like it. Good. All right. So yeah, so I'll only record the beginning part. We're actually talking about stuff, and then after that, I'll turn it off. Consider most of you guys are gone after like 10 minutes. Don't need 2 hours of just me sitting here doing nothing. So should be fine. Good. So today's lab deals with what's known as the electrostatic potential. So let's talk a little bit about that. And this comes from basically work and potential energy. So remember from 175 that if you have a force which is a conservative force, then you can define a potential energy from that. And the conservative force comes from the fact that the work is constant regardless of how far you move an object. Or basically saying that if you brought an object from an initial position back to the same position, there we go, the amount of work you would do would be equal to 0. So if I start off here at, say, point A, and I go around and I come back to the same point A, then the amount of work you did was basically equal to 0. And this is true when you have a conservative force, right? So a conservative force means that we can then define a potential energy. And we do this using the work, right? So we say then is that the work, which is then equal to the force times then the displacement times then cosine of the angle between the two is then equal to minus the change of potential energy. Oh yeah, you guys are used to PE. Sorry, let me change that. There we go. Write that in the way I should write it. Okay. So this is then equal to minus the change of potential energy. Right. Now, in this case, we have what's known as the electric force, which we'll see in a little bit. We can actually rewrite the electric force as being equal to the charge times then what's known as the electric field. Okay, we'll get there in a little while. But anyways, what this says then is that we can rewrite this then as the charge times the magnitude of the electric field times the magnitude of the displacement times cosine of angle between the two then is equal to minus the change of potential energy. Now, for our purposes, though, it's much more convenient instead of working with potential energy, which in this case would be the electrostatic potential energy, to define a new quantity, which is then known as the electrostatic potential. Okay? And the way we do that is we say that this is actually equal to then minus the charge times the change in delta V, where delta V here is what's known as the electrostatic potential. So comparing these two things together, what this means then is that the electrostatic potential, which we're going to call V, is then equal to the potential energy per unit charge. So this is what's known as the electric potential. So this thing then has units of energy, which is a joule, per that of a charge, which is a coulomb. So the electrostatic potential has this guy, but this thing gets a special name, and that special name is what we call a volt. Okay. So a major question is, well, why do we do this? Well, the answer to this is because we have things which will actually measure voltage, and that's what we call a voltmeter. So what a voltmeter does is, let's say, here's my voltmeter. So on here, there's a screen, and then there's usually a dial, and that dial we usually set to measuring voltage. So we're gonna measure, say, voltage. And then this has two leads. So we have one lead which comes out, and we put it at one spot. And then we have another lead which we put out here, and we're gonna measure something on here which says something like 1 volt, okay? What that means is that one of these we're gonna call 0 volts, and then the other one is gonna be at 1 volt. So basically what this means is that the electrostatic potential difference between this point and this point then is equal to a volt. But if I then take my voltmeter Again, so here's my voltmeter. And I put my one lead again here again, and I take the other lead and I put it, say, somewhere over here, then I might measure that this thing is then 2 volts. So what that means then is that this then has a potential difference, which is then equal to 2 volts. So basically, the reason that we do volts is that it's something that we can actually measure. But the meaning of a volt is, again, the energy per unit charge. So basically what it means is it is the amount of energy it would take for me to move my charge from this location to this location. So in this case, it would take 2 volts potential difference between the two, which then is the amount of energy I would need to move the charge from this location to this location. So ultimately what a volt means, or at least what a potential difference means, is that is the amount of energy necessary to move a charge from point A here to, say, up here to point B. So this is what a volt actually means. So basically it's the change of potential energy, or the amount of energy I would need to move that charge from this location to this location. And again, the reason that we use voltage is because we have this beautiful thing, the voltmeter, which allows us to measure these potential differences. So to us, what's most important is this delta V. Not necessarily what V is, but what delta V is. So delta V is what's known as the potential difference, or simply voltage. This is also known as voltage. Okay. Now, why do we care about voltage? Well, voltage is easy to measure, and because potential energy is a scalar quantity, then voltage is also a scalar quantity, which means it doesn't depend on direction. So voltage, oops, go away. There we go. So voltage is a scalar quantity, which means no direction. So unlike things like force, or as we're going to learn, electric fields, it doesn't depend on the direction. It only depends on that between each one of these two different objects. Okay. Now, why else do we care about voltage? Well, as I said, number one, it's easy to measure. Number two, it's a scalar. But number three is that it's intimately related to the electric field. So it's related to the electric field. So basically, if I can measure the voltage, then I can measure the electric field. So by measuring the voltage, I can indirectly determine exactly what is the electric field. Okay. And this is given by the relationship between the two, where we started, which is this expression here. So let's rewrite all that. So what we had was the charge times the magnitude of the electric field times then the displacement times cosine of the angle between the two is then equal to minus the charge times then the potential difference. Well, this charge is the same as this charge, so we can get rid of this. So what this says then is that the change of potential is then equal to minus the magnitude of the electric field times the magnitude of the displacement times cosine of the angle between the two. Or another way to write this is that the electric field itself then is equal to the change in potential divided by the change in position with a negative sign. So basically what this says then is that what? If I know what the potential difference looks like across a particular region, I can then determine the electric field by looking at how that potential changes from position to position.
What happened to cosine?
I'm sorry?
From delta V or whatever equals negative blah blah blah, and then the next step, what happened to cosine in between those two?
Oh, so in this case I'm assuming that it's only changing in the x direction. So sorry about that. So here I'm only looking at in the x direction, for example. So I'm kind of cheating and dropping that cosine at this moment. Because in general, this is 3 dimensions, but here I'm only looking at it in a 1-dimensional sense. So basically, I'm going from 3D down to 1D just to make it a little bit easier. Is that okay, Adrian?
I mean, I don't really see it. Like, I mean, I get what you're saying, but I'm also not picturing it. So
Okay. So basically, this is just saying that if my electric field, so we're using this one. So if my electric field pointed this way and I'm moving along in this direction of delta x, then this is the angle between the two. Okay. So basically meaning that just these two things don't have to be in the same direction. That's what this line is saying. Now, what I'm saying in this line is now I'm basically looking at the point where, okay, the electric field is this way, but my direction at which I'm changing is also in the same direction as the electric field.
okay, that makes it.
Okay, so basically, as I said, so what I'm doing is I'm going from a 3-dimensional sense like this down to a 1-dimensional sense and saying, okay, I'm only restricting myself to go in the same direction as the electric field.
Okay.
Okay, so what this thing is saying is what? If my potential, though, changes as I move along this, say, direction, what that means is there has to be an electric field. Okay, so meaning if at this point I had 2 volts worth of potential, and at this point I have 1 volt of potential, and I'd say this is the x direction, then since the potential is changing as I go from one point to another point, then an electric field has to exist. There has to be an electric field in this region. That's what this thing is saying. Okay, so if my potential changes as I go from position to position, then there has to be an electric field. Okay. Now, what this thing also says then is that the direction of the electric field points actually from opposite the direction of the change. So here, if I go from a low potential to a high potential, then this thing tells me then that the electric field actually points from high potential to low potential. So in this case, that means I have to have an electric field, which then points from the 2 volts down to the negative, or down to the 1 volt. Okay, so this is what the electric field does. So the electric field then points in direction from high V to low V. Okay. Now, what we're going to be doing in this lab is drawing basically potential lines. So we're going to be interested in what are known as equipotential lines. So let's talk about equipotential lines. So what an equipotential line is, it is a line where every point along that line has exactly the same amount of potential. So these are lines where every point along the line has the same amount of potential. So the same amount of V, okay? So for example, I might have lines that look something like this. So here is my one line, here's my other line, here's my other line. So these are then my equipotential lines. So these are equipotential lines. Now, let's go back to this expression. So what this expression says then is that what this cosine portion basically tells me then is that the electric field must be perpendicular to these equipotential lines. Okay? So ultimately what this expression tells me is that my electric field is perpendicular to the equipotential lines. Okay. So basically what that means is once I know what my equipotential surfaces look like, so these are my equipotential lines, what this means then is that my electric field at all points are perpendicular to these lines. Okay. So these are going to be my electric fields. So everywhere along here, my electric field then will be pointing perpendicular to all of these lines. So that means if I want to know what the electric field looks like in this space, all I have to do is draw these 90 degrees and then basically connect these 90 degrees together, and this is my electric field. So my electric field is going to look something like this. Okay. Now, if I want to know the direction of the electric field, all I need to know then is what? How does this thing change in equipotential lines? For example, is this 1 volt here, say 2 volts here, 3 volts here? Well, if it's something like this, then what I know is the electric field points opposite to the direction of the change, which means that in this case, my electric field will be pointing down in this direction. Okay, so it'll be going from high potential down to low potential. So these would then be my electric field lines. Okay. So this is what we're basically going to be playing with in this lab. So what we're going to do is we are going to draw these particular shapes, the ones that are given here, but I already set one up. So basically I'm going to be drawing these things. So this is going to represent what we call a parallel plate capacitor. So basically I have a plate down here which is negative charge and a plate up here which is then positive charge. Now I'm going to grab this thing out. So this thing initially was in here. So I'm going to pull this out and I'm basically going to put it at some location. So let's say I put it here. Then I'm going to go ahead and tap the draw line here. And that's going to draw these equipotential lines. So what this means is that everywhere along this particular green line has exactly the same amount of potential, which in this case is 55.92. Okay. Then I'm going to move it to another location. Let's say I draw it here, tap it again, maybe put it in here, tap it again, put it somewhere out here, tap it again. So what I want to do is draw enough of these equipotential lines to kind of get an idea of what these equipotential surfaces look like. Okay. So I want it to look something like this. Okay. Now, this is the first part of the lab. So for each one of these different diagrams that it shows here, you're going to basically draw each one of these diagrams and then do what we're doing here, simply move this guy around and draw a few equipotential lines to kind of get an idea of what it looks like. Now, in part B, what it wants you to do now is simply use these diagrams here and now draw the electric field on top of each one. So in this case, since this thing has high potential here, has low potential here, which you know is the electric field then has to point perpendicular to all of these lines, but going from high potential to low potential. So that means if I was going to draw in here, which I don't think I can draw in here, but let's see if I can. No, won't let me draw. So basically, if I was trying to draw in here, I would then draw a line which then points down, in this case, down through here, which would then point to the plate down here. So then I would draw some electric field lines using the fact that, again, it has to be perpendicular to each one of these lines, point from high potential down to low potential. And then if I want to check and make sure I did the right thing, I'm going to go ahead and push this button for the electric field, and then you can see the electric field points from high down to low. Okay. But I want you to draw it by hand first, and then go ahead and click this and make sure that what you did was correct, okay, just to kind of see what's going on.
Are those values on the bottom negative?
They are negative, yeah.
Okay, it's hard to see.
Yeah. Yeah, you'll see it when you actually see your own screen, but yeah, there's little negatives on here. So typically when you had a voltmeter, for example, it would set that this one down here would be at 0. So this up here would be at a higher positive value. So it would basically shift everything to 0 down here to say, okay, let's arbitrarily set this guy at 0. And then this guy is going to be basically the sum of these two numbers, right? So let's say this is at 100 volts. And this is at negative 100 volts. So ultimately this would be 0 and this would be 200 volts. So that's what your voltmeter would do. So it would just arbitrarily set the lowest one at 0. But here it's not quite doing it that way. So that's why we're not worried about the values. All we're worried about is which one is high and which one is low. So in this case, the electric field would go from the positive down to the negative. Okay. So that's basically all we're doing.
Without seeing the negatives, I was like, why are the arrows pointed that way then?
Oh. Gotcha. Yeah, hopefully when you see it on your screen, you'll see it a little bit better. Let's see if I make it bigger. And of course, everything I did just went away. That was great. So you can see that negative a little bit better if I make it bigger. Not really? Yes, okay. You can also see it here as I move this thing around.
On the voltage meter, yeah.
Exactly. So it says minus 9.96. So you can see it on there as well. So
Okay.
yeah. But anyways, like I said, so that's basically all you're doing. So you're drawing these equipotential lines. And again, the reason that we do the potential is that, again, it's a scalar quantity. It doesn't depend on direction. We can measure it using simply a voltmeter, and it's intimately related to the electric field by its change. So again, the electric field would point perpendicular to each one of these electric potential lines, and it would point, again, from high potential down to low potential. So by mapping out all of the electric potential lines for each one of these different scenarios, you can then determine exactly what this electric field looks like. So, and again, all you're doing in this lab then is you're drawing all 4 of these. Again, the way that you would do that is, so let's restart everything. Simply, you're just gonna turn on these. So let's turn off the electric field, turn on voltage, turn on values, turn on grid. And for example, let's say I wanted to make the second one here. So you would then just grab the positive charge and go ahead and throw this on here at some point. Right? And then grab the negative charges and pull these guys out. And then again, basically make these different scenarios. So once you have the different scenarios, again, grab this guy, pull it out, create your equipotential lines, draw these randomly at different locations, get some pretty lines. So you get something like this, and then again from here you try to draw your electric field. So again from here you need to be perpendicular at each location. So in this case I would draw a line going something like this, okay, which would point from the high potential down to the low potential. So basically that's it for this lab. So once you get all these lines basically set up on here, go ahead and take a screenshot or something like that. And then you can use Paint or whatever drawing software you have, and then go ahead and try to draw the electric field lines. And then from those, save those, and then just upload those onto Blackboard. So that's it. So that's all we're doing in this lab.
For the electric, I know it probably doesn't matter too much, but do you want us to do just like long arrows, or they had like the short little arrows, so I don't know how specific.
Yeah, no, here you can just draw kind of one continuous line that would do something like this would be fine. Yeah,
sure.
Yeah. So you don't have to do what they do here and draw an infinite number of little short arrows. So no,
great.
You don't have to do that. Yeah. So there's it. So here, also what they're trying to show on here is you can see some of these are fainter than other ones. So what they're actually drawing here is not only the direction, but the magnitude of the electric field as well. But we haven't quite talked about that. But if I go back here, stop it, there we go. This also tells about the magnitude here actually from here. So the faster the potential is changing with respect to position, the greater the electric field will become. So basically, if you think about this as the slope of the line, the greater the slope, the greater the electric field. So the faster the electric field changes from position to position, then the greater the electric field. So basically all that means is like here, the denser that these lines are, the greater the electric field would be changing. So that's basically all they're trying to show here. So like way out here where you see it's very faint.
So that electric field is the vector.
Correct. The electric field is a vector quantity. That's right. So it depends on both magnitude and direction. So the fainter it is the smaller the magnitude. And then the arrow is telling you the direction of that. But again, don't worry too much about that. All I want to know is, again, I want you to draw like one continuous line that kind of shows the direction. So again, you draw maybe this line that kind of does something like that. Okay. And again, so just using the fact that the electric field has to be perpendicular to all of these equipotential lines. So here, draw perpendicular, 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 and then connect all of those together and then say, okay, this is high potential, this is low potential. So then put the arrow pointing in, say, this direction. Okay.
So we only draw one of those lines?
Well, draw a few. You know, kind of draw maybe one here, one through here, one coming out here. So draw something like maybe 6 electric field lines or so, just so you can kind of get an idea what the electric field would look like over the space. Yeah. I think it says it in the manual here, how many you got to draw. But
Okay. Those marked up screenshots, those will be our data.
Yes, correct. Yeah. Yeah. So in this one, you're not doing any calculations or anything like that. I don't want to know the magnitude of the field or anything. So it's mostly just drawing these beautiful pictures, drawing your electric fields on over top of that. And like I said, just save those, upload those, and that's it. So nice and easy. Cool. Everyone's okay? Any other questions?
So we should have like 2 screenshots for each of the different things.
Well, one is fine, actually. Just give me one that has both the equipotential lines and your drawn electric fields. So each one can have both of those things on there. Yeah. And then once you draw the electric field lines, go ahead and click this guy and see, okay, were you right or not? Based off of what they say. So. And yeah, we'll get to talking about these things in class, hopefully next week, but we'll see what happens. This will be part of your second exam, so it'll be great. Okay, everyone is okay? So I said, so not too bad. So it's a little bit tedious kind of drawing these things. It takes a little while kind of dragging these things out one at a time, but that's not too bad. It doesn't take very long. It's not too difficult. So everyone's okay? Sounds good. All right. So in that case, I will stop sharing and stop recording.